Good morning everyone, this is Kannan Iyer and today I am presenting my research work on water retention behavior of unsaturated soils. This work was carried during my research secondment to University of Strathclyde as a part of European Commission project GREAT. My supervisors for this work were Professor D.N. Singh from my home institution IIT Bombay and Professor Alessandro Tarantino from my host institution University of Strathclyde. The special focus of study was to understand the water retention behavior of swelling clays during drying. The scope of research, this research is a part of joint research collaboration within the European Project GREAT, which is an international research staff exchange scheme project. As I discussed earlier, my home institution is IIT Bombay and my host institution was University of Strathclyde in Glasgow. And the work package under the GREAT project was climate change adaptation. My research secondment was completed during May to August 2014 at University of Strathclyde. And the main objective of my study was to understand the changes in soil suction and pore structure of swelling clay during its drying, and also try to see what is the relationship between the changes in soil suction and the pore structure. Before going further, let us understand about the mechanism of drying itself. Now, if a soil is saturated, that means the void space or the pore space within the soil mass is completely filled with water. Now, when the soil starts drying, the water gets replaced by air, and in this process, the suction develops within the soil mass. As the soil starts drying, we can see a thin film of water binding the particles, which has a potential which is lower than the potential of the free water. So in other words, the energy required to remove this water from the soil mass can be expressed as suction. So in a nutshell, we can conclude that when the soil dries, say from saturated state, it results in unsaturated state of the soil, because now the soil becomes multi-phase system. It also results in increase in suction and reduction in the moisture content of the soil. Now, soil will exhibit shrinkage during drying. This is more common in soils which have minerals such as montmolonite, for example the swelling clays, which exhibit significant amount of shrinkage during drying. Now, the shrinkage of soil causes volumetric reduction as well as changes in the pore structure, both in the size of the pores as well as the volume of the pores. So basically, with this understanding, what would be interesting is to understand how the changes in suction and changes in the pore structure are related to each other, especially from the perspective of swelling clay. Before proceeding further, I did some literature review trying to understand what are the factors which affect the relationship between suction and moisture content, which is known as the soil water characteristic curve, briefly termed as SWCC. So what I observed is the main factors which affect the SWCC are the initial density and water content, the stress history of the soil, the path of the SWCC, whether it is a drying path or a wetting path, and the hysteresis associated with these paths, the soil mineralogy, which mainly controls the shrinkage and swelling characteristics of the soil, and also the state of compaction of soil, whether the soil is undisturbed, that is the intact in situ soils, or initially slurried, for example mild tailings. Even the natural sedimentation process in water bodies can be represented by slurried samples, or the artificially compacted soils, for example embankments or any other structures which is created artificially. Further, some literature review on understanding the microstructure of the soils in different states also was carried out. And what I observed is most of these earlier studies have been focused on compacted soils and also to an extent on reconstituted soils, but very few studies on intact samples. So the challenges in front of me for this study was to understand the alteration in the pore structure during drying for soil samples from different initial states, the undisturbed state, the slurry state, and laboratory compacted state. And in other words, we can say that what is the effect of these different compaction states on the SWCC and the associated changes in pore structure during drying. So with these challenges, I selected a natural swelling clay which was collected from a depth of about 19.5 meters from western part of India in undisturbed state. The properties of this soil, it consisted of 70% clay content, plasticity index above 92%, and the specific surface area about 303 meter square per gram. And the major minerals were montmolonite and quartz. So the swelling nature of this soil can be attributed to the presence of montmolonite mineral. The testing methodology which I adopted for this study, soil was considered in three different compaction states. One is the initially slurried state. Here the initial water content was close to the liquid limit of the soil sample. Then the second state considered was the in situ state. From the natural undisturbed sample which was collected, undisturbed specimens were collected for the study without disturbing its fabric structure and pore structure. And the third state considered was the laboratory compacted state. In this state, the samples were compacted at two different water contents, 21% and 25% water content, and these compacted samples were further studied for their suction water content relationship and also the microstructure studies. For establishing the drying path SWCCs, dew point potentiometer was used. This instrument works on the principle of chilled mirror technique, and it measures suction indirectly based on the measurement of water activity, which can be converted to suction by using Kelvin's equation. The water content was measured by weight measurements during different stages of the drying. Now samples at different stages of drying were extracted carefully and then they were freeze dried and were used for measurement of the pore size distribution or the study of the pore size distribution by using the mercury intrusion porosimeter technique. The figure shows the relationship between suction and the water content for the swelling clay from intact, reconstituted and compacted states during its drying. These data points represent the water retention data for the reconstituted sample during its drying. These data points represent the water retention data for the intact samples during its drying. whereas the blue data points represent the water retention data for the compacted samples, compacted at 25% and 21% moisture content. What we can also observe that the water retention data for the reconstituted samples and the intact samples converge at some suction which can be defined as a critical suction, and beyond this point the water retention data or the soil water characteristic curve is almost similar for the reconstituted and intact samples. What we can also observe that the suction for compacted samples at a particular water content is lower than the suction for reconstituted and intact samples. We'll try to understand why this occurs from the understanding of the pore size distribution of the samples from these three different states. The points I1, I2, I3 and I4 represent the stage of drying at which the samples were extracted for the MIP studies for the intact samples. R1, R2, R3 and R4 indicate the stage of drying at which samples were extracted for MIP studies for the reconstituted samples, and C25 P1 and C21 P1 represent the samples taken for MIP studies at initial compacted states, compacted at 25% moisture content and 21% moisture content. C25 P2 and C21 P2 represent the compacted samples compacted at 25% and 21% moisture content respectively in air dry condition for MIP studies. Now let us try to understand the pore size distribution characteristics of the swelling clay for the undisturbed or intact samples. I1 represents the initial undisturbed state of the sample, whereas I4 represents the air dry state of the sample after completion of the drying cycle. I2 and I3 represent the intermediate stage of the sample during drying. This figure shows the cumulative pore size distribution, volume of the pores expressed in terms of void ratio and versus the diameter of the pores, and this curve represents the incremental pore size distribution expressed in terms of change in void ratio. What we can see is that the intact samples exhibit bimodal pore size distribution during its complete drying path. Now this bimodal pore size distribution has one cluster of pores as the interaggregate pores and another cluster of pores as intra-aggregate pores. What we can also see is the shrinkage of interaggregate pores as well as the intra-aggregate pores. The interaggregate pore shrinks from about 33 micron dominant pore diameter for the initial stage to 27 micron dominant pore diameter for the air dry state, whereas the intra-aggregate pore shrink from 0.022 micron for the initial stage to 0.008 micron for the air dry state. Also, what we can see is significant reduction in the volume of pores for both interaggregate and intra-aggregate pores. Now if we try to superimpose the water ratio, which is the ratio of volume of water to the volume of solids, on the cumulative pore size distribution curve, and if we also represent the macroscopic void ratio, which is the void ratio of the sample which can be obtained from the mass volume relationships by knowing the specific gravity and the dry density or the weight and volume of the sample, dry weight and the volume of the sample. So on superimposition, what we see is that the water ratio is similar to the void ratio for samples I1 and I2, which indicates that the samples are fully saturated. For sample I3, the water ratio value superimposed on this curve intersects at about 0.1 micron pore size, which indicates that the pore diameter or pores smaller than this size are saturated and the pores larger than this size are unsaturated. For sample I4, the water ratio value superimposed on the cumulative pore size distribution curve intersects at about 0.02 micron pore size. So the pores smaller than this size appear to be saturated, whereas the pores larger than this size are unsaturated for this sample. Now if we observe the pore size distribution characteristics for the reconstituted samples, this curve indicates the cumulative pore size distribution for the initial slurried or reconstituted sample, whereas this curve indicates the pore size distribution curve for the air dry sample. What we can see is a monomodal pore size distribution for the reconstituted samples, and the pores shrink both in size as well as volume during drying. Now if we superimpose the water ratio on the cumulative pore size distribution curve, what we observe is the water ratio is almost same as the macroscopic void ratio for samples R1, R2 and R3, which represent the initial slurried and the intermediate stages of drying, whereas for sample R4, which represents the air dry condition of the sample, the value of the water ratio superimposed on the pore size distribution curve intersects the curve at 0.00 at 0.012 micron. So what it indicates is that the pores smaller than this size are saturated, whereas the pores larger than this size are unsaturated. Now the similar inference is for the compacted samples. The compacted samples also exhibit bimodal pore size distribution, and what we observe is some shrinkage in the interaggregate pores and significant shrinkage in the intra-aggregate pores. Now if we try to compare the inferences from literature, Lee and Zhang in 2009 published a work where they attributed the reduction of the interaggregate pores mainly to the mechanical compaction effect, and the reduction in the intra-aggregate pores to the hydraulic effect during drying. These inferences are quite similar to what we observed during our study. Also, if we superimpose the water activity on the cumulative pore size distribution and also represent the macroscopic void ratio, what we observe is that the initial compacted samples, compacted at 21% and 25% moisture content, are fully saturated, as W is almost same as E, or the macroscopic void ratio, whereas for the air dry states of these compacted samples, some of the pores are unsaturated. So the superimposition of the value of water ratio on the cumulative pore size distribution curve indicates that the samples air dried from initial 25% moisture content compacted appears to have the separation of saturated and unsaturated pores at about 0.055 micron, whereas samples compacted at 21% moisture content after air drying indicates that the pores smaller than 0.036 micron are saturated, whereas the pores larger than this size are unsaturated. Now based on this, if we try to infer this data from a different perspective, if we represent these data points based on the Laplace equation, which relates the pore diameter with suction, this indicates that for a particular pore size, the capillary pressure developed will be given by this equation, and if water has to be removed from the pore, then a suction or a pressure which is greater than the capillary pressure given by this equation is required. So in principle, if a point lies below this curve, it indicates that the point the pore is saturated as the suction or the pressure is less than the threshold pressure required for desaturation of the pore. Any point above this curve will indicate a desaturation of the pores. So now if we try to superimpose the experimentally obtained dominant pore diameter and the experimentally obtained suction for the intact and reconstituted samples, these data points represent the dominant pore diameter suction relationship for intact samples, whereas these data points represent the dominant pore diameter suction relationship for reconstituted samples. What we can observe is for samples I1, I2 and I3, which represent the initial stage and intermediate stages during drying, for intact samples the data points are below the curve given by Laplace equation. For reconstituted samples also, samples R1, R2 and R3 have the dominant pore diameter suction relationship below this curve. So it indicates that samples R1, R2, R3 and samples I1, I2, I3 are saturated, or all the pores are saturated. Now in the air dry condition, sample I4 and R4 have the dominant pore diameter suction relationship above this curve. So it means that part of the pores are unsaturated. Now if we intersect the line joining these data points with the curve giving the Laplace equation, this indicates the point of desaturation. So for intact samples, the desaturation is expected at a suction of 22 megapascal, which corresponds to 0.012 micron pore diameter. Now if we compare it to MIP results, it indicates that the dry sample has pores larger than 0.02 micron as unsaturated, which is quite close to the value inferred from this curve or this figure. For the reconstituted samples, desaturation appears to happen at about 45 megapascal suction, which corresponds to 0.007 micron pore diameter. This is quite close to 0.012 micron pore diameter obtained from the inference of MIP results, which separates the saturated and unsaturated pores in the dried sample. What also can be concluded is that for the intact and reconstituted samples, there is a progressive shrinkage of the pores or the deformation of the pores. So as the samples are drying, the water spills out from the pores and simultaneously the pores shrink. Now during the shrinkage, the pore diameter reduces and now these pores can sustain higher suction. So higher pressure is required to evacuate or remove water from these pores. So as at a particular suction, these pores remain still saturated. Now as the drying process continues and suction increases and the pressure or suction exceeds the capillary pressure which can be sustained by these pores, there is further spillage of water and further shrinkage of these pores, and this process continues until these pores can shrink further, and as the shrinkage ceases, the pores become unsaturated. Now this hypothesis appears to be quite valid for swelling clays in its intact and reconstituted states. So now if we try to understand on similar lines for the compacted samples, the actual data points for the compacted samples are plotted along with the curve given by the Laplace equation. For the initial state of the sample, both samples compacted at 25% and 21% moisture content, the samples are saturated as the data point lies below the curve given by Laplace equation, whereas the air dry condition indicates that part of the pores are unsaturated. The point of desaturation for samples compacted at 21% moisture content is about 15, is corresponding to 15 megapascal suction, which corresponds to about 0.02 micron pore size. The pore diameter which separates the saturated and unsaturated pores from MIP results is about 0.036 micron, which is quite close to these results. For samples compacted at 25% moisture content, the threshold desaturation point is about 10 megapascal, which corresponds to 0.028 micron pore diameter. The desaturation point, or the pore size separating the saturated and unsaturated pores from MIP results, comes to be about 0.055 micron, which is comparable to inferences from this graph. So based on these studies, we can hypothesize a deformable capillary tube concept for the swelling clays. Now, if this curve represents the curve given by the Laplace equation for soils which exhibit non-deformable pores which are initially saturated, the relationship between pore diameter and suction will remain below this curve given by Laplace equation to a certain stage, and then it will cross this curve which indicates desaturation of the samples, and beyond this stage more and more pores become unsaturated. But now if we consider the case of deformable pores, where the pores try to remain saturated during the process of drying, as we observe for the swelling clays, the curve relating the pore diameter and suction will remain below this curve until a stage when the pores cannot shrink further and would desaturate. Now this kind of behavior is observed for the swelling clays, especially for intact and reconstituted samples. So it is opined that a deformable capillary tube concept is required for understanding the drying process and the suction characteristics during drying for swelling clays. So we can conclude from this study that the drying path SWCC of the swelling clay in its compacted state exhibits lower suction as compared to samples in intact and reconstituted states at a particular water content. This can be attributed to higher percentage of interaggregate pores in compacted samples as compared to intact and reconstituted samples. So in other words, it can be opined that both the interaggregate and intraaggregate pores influence the water retention behavior of the compacted soils. For swelling clays, it is also observed that the intact and compacted samples exhibit bimodal pore size distribution, that is, a cluster of interaggregate pores and a cluster of intraaggregate pores during drying. Whereas the samples dried from reconstituted state exhibit monomodal pore size distribution. Also, it is observed that this water retention data of the samples dried from intact and reconstituted states converge beyond a certain value of suction, which can be defined as critical suction, and this convergence can be attributed to shrinkage of the pores, further leading to similar residual pore size distribution during drying for both intact and reconstituted states. Here I would like to add that for air dry samples of samples dried from intact and reconstituted states, the dominant pore size diameter are quite comparable. For intact samples in air dry condition, the dominant pore size diameter is close to 0.008 micron, whereas for reconstituted samples the dominant pore size diameter in air dry condition is 0.007 micron. So this supports the hypothesis of convergence of the pore size distribution during drying for intact and reconstituted samples. However, there is a need to do further studies in order to validate this hypothesis. Also, it is opined that a deformable capillary tube concept may be suitable to explain the suction characteristics of swelling clays. However, generalization of this hypothesis would require more studies on similar soils. Also, it is opined that there is a need to understand the changes in suction and the changes in the pore size distribution during the wetting path for such soils. So there is a scope for further research. So studies are required on different swelling soils in order to validate the hypothesis of the deformable capillary tube concept for swelling clays during drying. So I would like to acknowledge the support of the European Commission via the Marie Curie IRSES project GREAT, which stands for Geotechnical and Geological Responses to Climate Change, exchanging approaches and technologies on a worldwide scale. I also wish to acknowledge my home institution IIT Bombay and my host institution University of Strathclyde for their support during my research secondment at University of Strathclyde, which I completed during May to August 2014. I express my sincere acknowledgement to Professor Alessandro Tarantino from University of Strathclyde and Professor D.N. Singh from IIT Bombay for their guidance and support during my research secondment. I also express my sincere thanks to colleagues and staff at University of Strathclyde and IIT Bombay for their support during my research secondment. I thank you all for your patient listening.